Yeah, well, hello everyone. Thanks for the invitation to share a, a podium and talk about Santorini. So my name is Michele Paulatto. I am a research fellow at Imperial College, currently funded by the Rio Tinto Center for Future Materials. Um, I will give an overview of the seismic imaging results at Santorini volcano that have come out over the last 6 years or so. And this is work that involves a large group of people. A lot of the grunt work was done by a number of students, Ben Heath from the University of Oregon, Kaikan Krapkiewicz here from Imperial, Bernard McVeigh, and others as well. And also with lots of colleagues, most notably Joanna Morgan, Emily Hooft, who led the marine campaign. So this is the Proteus experiment. Proteus stands for Plumbing Reservoirs of the Earth under Santorini. And I'll give you a little bit of history about it. So in 2013 or so, I was relatively fresh out of my PhD, having worked on imaging Montserrat. And I thought, well, it'd be good to do another campaign on a volcano, and Santorini would be a great target. So I went to talk with Joanna Morgan and said, well, would it be possible to do full waveform inversion on Santorini? And first thing that she told me was, you're too late. There's a group of Americans who've already got funding in place to go and do a big campaign. So that was Emily Hooft and the NSF grant that funded the Proteus experiment. And then Joanna got a add-on grant from the Leverhulme Trust to pay for the land stations and do the full waveform inversion. But I was the ideal candidate to actually do the work. So Joanna ended up hiring me to do some of this and work on the full waveform inversion. So it's been a really great group effort and definitely one of the best active source experiments at any volcano. It involved deployment of 91 ocean bottom seismometers around Santorini. You can see the map on the right with the yellow dots, plus a bunch of land stations on the islands of Santorini, of Thera, Theracia, and the Camini, and nearby Anafi. And shooting along a dense and regular grid, and you can see that's the black lines on the right. So the idea here is to have long offsets, up to 100-kilometer offsets to image deep. And that's why we have this ribbon shape to the experiment rather than a square. The motivation is quite obvious. For anybody who's tuned in today, obviously we wanted to understand the late Bronze Age eruption at BA and understand the likelihood of future eruptions of the same magnitude or smaller. Particularly, the interest was piqued by the 2011-2012 seismic crisis, which caused also deformation around the caldera, as shown by Parks et al. Here on the right. So in particular, we wanted to see where the magma is today, what's the current status of the magmatic system, how much of it there is, in which conditions it's being stored. So the first results from the experiment were the travel time tomography. This is the earliest paper, this Hooft et al. 2019, showing a P-wave velocity model. On the left here is two cross sections with absolute VP on the top and relative P-wave anomalies on the bottom, only showing the top 3 kilometers. So just a shallow structure. And the main feature here is this low velocity inside the caldera. At about 2 kilometers depth is quite significant. And we interpreted this as some intra-caldera breccia and Ingredients deposits formed by the final stages of the LBA eruption and the collapse of the caldera floor. But there may be more to it, and there may be some role of the hydrothermal system in creating that low velocity anomaly as well. In the following year, Brenna McVeigh, who is a master's student at University of Oregon, published a deeper model, well constrained to about 6 kilometers. And I'm showing here two cross sections again, going across a Santorini caldera in two different directions. And this deeper look showed there's another low velocity anomaly below that, the one I showed in the previous slide. It's weaker, but still significant, since it's minus 21% VP compared to the background, at 3 to 5 kilometers depth. And if we interpret this as melt, which is our most likely interpretation, that would be about 4 to 13%. Not a huge amount, not a big magma body, but robust in the imaging. So this would be the magma reservoir that was replenished in the 2011-2012 event, and that anomaly corresponds very, very closely to the source of the inflation observed from GPS and INSAR data. There's also some hints of a possible links with the Colombo system. This is the cross section from southwest to northeast, so going from the caldera out to the northeast towards Colombo. And we see there's kind of a series of low velocity anomalies, essentially linking the two systems. There wasn't in this early model a significant low velocity anomaly under Colombo, but we'll see more about that later. Now, behind all this, a lot of the work was done by Ben Heath, who did a lot of the picking of the travel time tomography at the University of Oregon. And in 2021, it published an inversion still of the travel times, of the active source P-wave travel times, but with azimuthal anisotropy. So meaning that P-wave velocity is a function of azimuth. And on the map here, you can see the velocity anomalies plus the direction, the fast direction of the P waves, so that the little bars of the fast direction of the P waves at 3 kilometer depth. And there's a bit of variability, but the main trend is that the fast velocity aligns with the regional faults, is perpendicular to the regional extensional stress, which is northwest to southeast here. There isn't localization of particularly strong anisotropy where the magmatic features are, so along the Colombo line, for example. But it's widespread anisotropy, so probably linked with fracturing of the upper crust, rather than specifically to magmatic intrusions. But yeah, there's this alignment between the anisotropy, the magmatic features, and the tectonic features, showing that there's clearly an interaction between magmatic and tectonic processes here, as was already suspected, seeing the surface geology. So the next step was the full waveform inversion, and this was the work done by myself and Kajetan Krapjevic with Joanna Morgan here at Imperial. So full waveform inversion, as opposed to travel time tomography, uses the full waveforms recorded by the seismometers and matches the amplitude and phase, and not just the travel times. I won't go into the detail of the method, but for those in the know, we used an acoustic isotropic for solver, which means that we get only P-wave velocities from this inversion. We don't get S-wave velocities. And it's a standard adjoint method to get the model update. The main advantage of waveform inversion is its better resolution. So it's about half the wavelength. If you do it right and you've got the right data, the resolution can be significantly better than for travel time from travel time inversion. So we use frequencies of up to 6.5 hertz. Half wavelength for those frequencies is about 200 to 500 meters. Equivalent resolution for travel time tomography would be 1.5 to 3 kilometers. So that's a significant improvement, and we'll see what that does to the output. But most importantly, for volcano imaging, travel times are not very sensitive to low velocity anomalies. showing this on the right with some plots that we made for a paper that came out in 2002, showing the propagation of a wave in a homogeneous background with a low velocity anomaly. And it shows the delay in the wavefront going through that low velocity and how that wavefront heals as we move further away. So if you're just measuring the travel times, you can't capture that velocity anomaly. This one is half the wavelength. This one is bigger. It's twice the wavelength. But the wavefront still heals. You would detect a low velocity anomaly, but you would not recover the full amplitude of that anomaly by inverting travel times. What waveforms do is they allow you to use all of these secondary arrivals and the amplitudes, and they allow you to recover the full anomaly. So travel times can tell you what the melt is, but they can't tell you how much melt there is. They're a poor indicator of melt fraction. So the FWI, the target initially was to invert the whole data set. We found out that it was quite difficult because of the computational cost of inverting such a large data set, the gaps in acquisition around the islands, the low signal-to-noise ratio for the long offsets, etc. So we focused instead on Columba volcano for the full waveform inversion. So a subset of the Proteus data set that is fully offshore, centered on Columba. That's Columba there, actually a little to the top left of the model box. So this was the initial model for the full waveform inversion from the travel time inversion by Ben Heath. And we can see the Columba crater there. There's a hint of a low velocity anomaly at the bottom there, but it's not very clear. That's the full waveform inversion output at 3 Hertz, and that hint of a low velocity is starting to deepen. And then we've got the output at 6.5 Hertz. It's a lot more detailed. There's certainly a bit of noise. We're introducing some artifacts, but we've got this very clear, strong low velocity anomaly right under the crater that is very robust in our inversion. So actually go back to the travel time model and then forward to the full waveform inversion output. So we've interpreted that as a small but high melt fraction magma reservoir. It's about a cubic kilometer in size. It has a melt fraction of 20 to 45%, so significantly higher than what we find on the Santorini with travel time tomography. If we take those velocity at face value, which is 3.5 kilometers per second. And this was undetected previously with travel time inversion. Working with Florian Schmidt, we also showed that that reservoir lies at the tip of a cone-shaped region of earthquakes. And this is a swarm from 2006-2007, indicating that some of these swarms are likely to correspond to Daikin events that would replenish these very shallow but small magma reservoirs. So since then, there's been a couple of new studies that came out really recently from Emily Hoof's group, and I have not been involved in that work directly, but I'll talk about them briefly for completeness. So there's the paper by Autumn et al. Came out a few weeks ago. They added PMP phases to the travel time inversion. So we're going back with the travel times, but not just using refracted waves, but also using MOHO reflections. So that allows them to look deeper, because the refracted waves bottom out at about 6 or 8 kilometers depth, while the PMP reflections go all the way down to the MOHO and bounce back. What they see is a high velocity route. They also constrain the MOHO depth, which is around 26 kilometers, with a high velocity route under Santorini. And there's a number of low velocity anomalies in the middle crust to the east of Columba at about 10 kilometer depth. So some really interesting additions constraining the intermediate and deep parts of the system. And then another paper that came out also very recently by Huff-Stettler et al., also from Emily Hoof's group, added again, to the P wave travel times added local earthquake arrival times, so both P and S wave arrival times. This is the ray coverage for the active source and local. So this is the P waves arrival times. So it's active source and earthquakes together, and these are the S wave travel times and ray paths. Sorry. So these are just from the earthquakes. So inverting those together, she gets a P wave velocity model and an S wave velocity model. This is a cross section going through the caldera there, Santorini caldera and Colombo. Absolute velocities there, velocity anomalies here. This is the low velocity under the Santorini caldera that we've imaged before. And there's this large low velocity anomaly at about 8 to 12 kilometers depth east of Colombo in the P waves, and then something similar in the S waves as well there. So this is the current view. Another image from the Autometal paper, showing kind of everything together, really. The small, shallow, low velocity
Michele,
anomalies between. Yeah.
Can you please wrap it up in the next minute?
Yes. Thank you. Last slide. Under Santorini and Colombo, some mid-crustal reservoirs, 8 and 10 kilometers depth, and some high velocities at the bottom of the crust. The connections between these reservoirs is still a bit uncertain. There's clearly a connection, though, with the recent seismic crisis, and Jens is going to talk more about this. We saw the connection with Colombo in the 2006 swarm, but the 2025 swarm seemed to perhaps radiate from one of these mid-crustal low-velocity anomalies east of Colombo. So that's my conclusions. We got some small reservoirs. There isn't a large reservoir shallow, so small, very unlikely chance to have large eruptions. And these mid-crustal reservoirs, though, which are very interesting and related to the tectonic environment as well. Thanks, that's all.